So I'll let you read this problem for a moment. Feel free to pause the video and then let's think about this problem. So in this problem, what's happening is you have a rod which is pivoted around one end and it's hanging vertically. The length of the rod is L and the mass of the rod is M. You take a piece of putty and you shoot it at the rod and it sticks to the bottom of the rod. Let's make this a little larger. Sticks to the bottom of the rod and the whole thing starts rotating. The first thing that you need to find is the angular velocity of the rod immediately after the collision. So you have to find the omega the moment it hits the bottom of the rod. And the second thing you have to find is how high does the end of the rod rise. Okay. All right, so let's focus on the first part. So for the first part, we can use conservation of angular momentum. So remember that conservation of angular momentum applies when the net torque of a system about a certain reference point is 0. When the net torque is equal to 0, L is conserved. Generally, if a system has a natural pivot point around which it's rotating, and you calculate all the torques and angular momenta relative to that pivot point, then the net torque will be 0 and angular momentum will be conserved. So the point of this is that if the system has a natural pivot point, that's a very good point to choose as your reference point, because the angular momentum is going to be conserved about that point, right? So we're going to choose the pivot point over here, let's call it O, as our reference point for calculating angular momenta. And if we do that, we can be sure that the angular momentum is going to be conserved about that point, because the net torque about that point would be 0. Okay, so let's go ahead and calculate the angular momentum. So we're going to do a calculation very similar to our conservation of momentum calculations. We're going to set the total angular momentum before equals the total angular momentum after the collision. So before the collision, it was only the point mass that was moving that had angular momentum. What is the angular momentum of this point mass? So this is a point mass moving in a straight line. So its angular momentum can be found from r perpendicular multiplied by p. So p is the momentum of this point mass, it's going to be mv, and r perpendicular would be this distance. So you draw a line through the momentum vector, make a perpendicular from the reference point to that line, and the length of that perpendicular is the lever arm, or r perpendicular. Clearly, that's just going to be equal to L. So the angular momentum of the point mass before the collision is just going to be mv multiplied by L. Now, once the point mass gets stuck at the bottom of the rod, and both the point mass and the rod start rotating, we can then both of the point mass and the rod have angular momentum, right? So for that, you use the formula I times omega. So what is the I of this whole system? It would be the I of the rod plus the I of a point mass that's going in a circle. So the I of this rod is going to be 1/3 ml square, and the I of a point mass going in a circle is just going to be little m L square. And so that's the total I of the system times omega will give you the angular momentum of the system, right? And so now we can just solve for omega. So omega is going to be mvl divided by 1/3 capital M L square plus m L square. And you could probably simplify that a little bit. Okay, and why did I use 1/3 ml square and that is because that is the I for a rod that's rotating around one end. So that's so that we saw earlier in chapter 9, I think, that turns out to be 1/3 ml square. Okay, so that is your omega. The last thing that I'm going to talk about is a few applications, a few practical applications of angular momentum. So the conservation of angular momentum has several fascinating consequences. One consequence is the gyroscopic effect, right? So this device over here is called a gyroscope. Notice this uh, thick disc over here, which is encased inside in all these rings, and this disc is connected to a cylinder, which is the blue cylinder over here, and they can rotate together, right? So typically this disc is set into motion. There's a little blue arrow here showing the omega. So that shows you how the disc, how the thick ring rotates together with the cylinder that it's connected to. Now this thick ring has a large moment of inertia. So once you start it rotating, it has a lot of angular momentum, because angular momentum is I times omega. I is large for it, and omega is also large if you set it rotating very fast. So I times omega is going to be pretty large, and so it will have a significant amount of angular momentum. Now, if there is no friction, then there is nothing to change that angular momentum, right? And so the angular momentum will remain conserved because there is no external torque on that system, right? So if the angular momentum is conserved, remember that angular momentum is a vector. So a vector being conserved means its magnitude is conserved and its direction is conserved, right? So since the direction of the vector is conserved, this ring and the cylinder at the center of it will always, while it's spinning, it will always want to point in the same direction, right? So that is very, very useful, because this ring and the central cylinder are gimbaled, and so the rest of the apparatus can rotate, but these can continue pointing in the same direction. So as you can see in this diagram over here. So once you set this central disk to rotate, it will always keep pointing in the same direction. So as you can see, it's pointing in the same direction, pointing in one direction over here, and it's pointing in the same direction over here, even though the rest of the apparatus has been rotated, right? So what do you think is a use for this? So one very important use for this is that it can be used in navigation. So you point it in a certain direction and set it rotating, and then it will always point in that direction, even though the rest of the apparatus can change its orientation. So this is very, very useful in ships and planes. Now, ships and planes use gyroscopes a lot to ensure to keep track of which is the correct direction, because when you're in a plane, it's very difficult to every direction looks the same. So or if you're out in the ocean, then every direction looks the same. So a gyroscope can be used to keep your bearings. Okay, another application of this is when you pitch. I always forget what sport this is. I assume this is a football. So when you pitch a football, if you give it a spin, then the football will keep pointing in the direction of its spin. So in this case, this football has been given a spin indicated by this curved arrow here, omega, and so it will keep, it will have an angular momentum which points in the direction uh, uh, shown by this arrow. Now let me just mention one other thing here, which I don't remember if I mentioned earlier. Suppose an object is rotating. Suppose you have a sphere that's rotating around this axis. Actually, let's use this. Let's use a different example. Suppose you have a disk that's rotating about an axis which comes out of the page. and it's rotating in this direction, right? So the angular momentum L was I times omega. So from this formula, you can see that L will have the same direction as omega. As long as I happens to be an axis of symmetry, you have this formula. So L is equal to I times omega. And you know how to find the direction of omega, right? Using the right-hand rule. We talked about that back in chapter 9. So how do you use the right-hand rule to find the direction of omega? You curl the fingers of your right hand in the direction of rotation, and your thumb points in the direction of omega. So the same thing applies for L as well, because L and omega will have the same direction. So you can use the right hand rule to find the direction of the angular momentum. Okay, so that is why for the gyroscope, if the gyroscope, now you can understand why the direction of the angular momentum vector is the way it is for both the gyroscope and the football. Okay, another application, similar application is bullets. So when a gun fires a bullet, typically you would want the bullet to maintain a particular orientation. You don't want to be flacking around. So how do you make the bullet keep pointing in the same direction as it's flying through the air? The barrel of a gun is grooved. And so the spiral grooving inside the barrel of a gun allow causes the bullet to spin while it's moving through the barrel of the gun. And so by the time it emerges from the barrel of the gun, it has a pretty high spin. So it has a large angular momentum. And so since the external torque on it due to friction, air resistance is very, very small, the angular momentum of the bullet is essentially conserved. And so its angular momentum vector keeps pointing in the same direction, and the bullet maintains its orientation. Okay, now there are many, many applications of gyroscopes. I mentioned navigation, ships, and planes, but there are many other applications as well. One other application is that if you are using a camera to take a picture, then you want your camera to be pointing in the same direction. However, if you're walking around while taking the picture, or if you're in a helicopter while you're taking the picture, then there's a chance that your camera will move around a lot, and so the image will not be pleasant to look at because the camera was bumping and jerking and moving around a lot. So in order to always make your camera point in the same direction, you can connect it to a gyroscope. And those are called gyro cameras, and they're used a lot in filming movies. So here's an example of a gyro camera. The camera is connected to is mounted on a helicopter, but as you can see, the helicopter might be moving around, but the camera always points in the same direction. So it's a gyro stabilized camera. Okay, now what is the result of taking a picture with a gyro stabilized camera? Let's take a look at that. So on the left side, you can see what happens if you just have a camera which is not stabilized and you're walking along and running the camera. And on the right side, you have a gyro stabilized camera, and you can see the difference in the image when the camera is stabilized. All right, so that's one class of applications. Another class of applications of angular momentum conservation is the following. L equals I omega. L equals I omega, right? So if L is conserved, I'll just write this again. If L is constant, now for some reason, suppose I changes. Let's say I goes up or goes down. Let's say that I goes down. What must happen to omega if L has to be constant? The answer is that omega has to go up, right? So if the I of a rotating system goes down for some reason, the omega of the rotating system has to increase, which means that it will rotate faster. If the I increases, the omega will go down, and it's going to rotate slower. So L is equal to I times omega. Let's look at an example, an application of that. Here's an ice skater, and I'll let you watch. So, did you see what happened? So, she was at first spinning slowly, but she had her arms and legs spread out, and so her eye was larger. Remember that more mass distributed away from the axis of rotation gives you a larger eye. So, the eye was larger. Then she brought her arms and legs close to her axis of rotation, and that made her eye smaller. So her omega has to go up to conserve angular momentum, and so she started spinning really, really fast.
There's another really fascinating application of the fact that if L is constant, then for a rotating object, if I changes, then omega must correspondingly change. So that has to do with our solar system. So if you think about our solar system, notice that all the planets more or less orbit the sun in the same plane and also in the same sense. So, why is it that all the planets chose to orbit the sun in one particular plane? And also, why do they all orbit in the same sense? Like, why don't some of them orbit the other way? That has to do with how the solar system formed. Right. So let's just very, very briefly talk about the fascinating history of the origin of the solar system. So it is believed that the solar system started out as this one huge, gigantic cloud, a cloud of gas and dust. And what was the size of this cloud? The size of the cloud is believed to be something like 100,000 astronomical units. One astronomical unit is the distance between the Earth and the Sun, and it's 93 million miles. It's a commonly used yardstick in astronomy. What is the current size of the solar system? The current size of the solar system is about 100 astronomical units. That's the current size of the solar system. So the cloud from which the solar system formed was this gigantic cloud of gas and dust, uh, which, uh, which had a size of 100,000 astronomical units. Now it's believed that something made this cloud unstable. So previously the cloud was stable because the inward force of gravity was perfectly balanced by the outward pressure of the gas and the dust. Um, Something made this cloud unstable, and as a result of that, it started collapsing inwards. So the whole thing started collapsing inwards. We don't exactly know what made this particular cloud unstable, but there are a few possible explanations of things that could make this unstable. And so the result is that the cloud started collapsing under gravity. Now, this cloud would most likely have had some angular momentum or some rotation before the collapse happened. It would be very strange if it didn't have any rotation at all. That would be a very strange situation that the there is the angular momentum of this cloud is exactly zero. It would have had some very small amount of rotation before the collapse happened. Now, what's going to happen to that rotation rate as the cloud collapses? Let's say that, okay, so the cloud is collapsing, right? And let's say that the original rotation that the cloud has had was around this axis. So the cloud was rotating around this axis in the beginning as the collapse began. So what's going to happen to its rotation rate? Well, as the cloud is collapsing, its size is decreasing, right? Its mass stays the same, but its size is decreasing. So the cloud is getting smaller. So what is happening to I if the mass stays the same, but it's getting the distribution of the mass is more compact about the axis of rotation? What happens to I? So large I means more mass spread far away from the axis of rotation, as we learned in class. So if the mass is now getting more compact about the axis of rotation, I is coming down, right? So as a result of the contraction, I goes down. What happens to omega? Omega has to increase because the total angular momentum of the system will remain the same because there is no external torque on the system. So if L is constant, I goes down, omega has to go up. So what that means is that as the cloud collapses, it's going to spin faster and faster. So initially it was spinning very, very, very slowly, negligibly slowly. But then as it starts collapsing, it's going to spin faster and faster and faster. And as I gets smaller, omega increases even more. So it's going to keep on spinning faster and faster. Now, there's another fascinating thing that happens with uh, regard to the collapse of the cloud. So it's easy for the cloud to collapse in every direction except for along the plane of rotation. So if this is the plane of the equator of the cloud, so if this is more or less the central part of the cloud, so it can easily collapse in every direction except along the direction of rotation. So basically what happens is that all of these portions of the cloud will collapse. They won't have much trouble collapsing, but the central disk, the equator of the cloud, that will not shrink. And that is again, that has to do with conservation of angular momentum, right? So basically what's going to happen is the cloud will eventually turn into this swirling disk of gas and dust. So it's going to assume this pancake shape. So it will turn into this swirling disk of gas and dust. So initially it was this huge spherical mass, and now it's turned into this disk of gas and dust, and which is rotating very, very rapidly. The central part of this disk of gas and dust, the temperature will be the highest at the central part of this disk of gas and dust, and that will turn into the sun, and the other parts of the disk eventually will turn into the planets. And so the planets inherit the angular momentum of the cloud, and so the planets will also be rotating in the same sense in which the cloud was rotating. And so that is how the solar system formed. And that also explains why the planetary orbits are all more or less in the same plane. And yeah, so and you also understand why everything is rotating in the same sense as well, because everything inherited their rotation from the rotation of the cloud.
Okay, so that's the second class of applications. The third category of applications of angular momentum is that if you have a composite system with different parts that can rotate, if the angular momentum of one part of the system changes, but the total angular momentum of the system is conserved, then the angular momentum of the other part of the system must change in a certain way in order to make the total angular momentum zero. So, what's an example of that? One example of that is a helicopter. So, suppose just imagine a helicopter that's sitting on the ground, and it's not rotating, the blades are not rotating. So, the helicopter is at rest. Now, suppose the blades are turned on, and so they start rotating, the rotors start rotating really fast, and the helicopter takes off. What was the angular momentum of the helicopter before the rotors were turned on? The answer is zero because everything was at rest. After the rotors are turned on, let's say the rotors are rotating like this. What is the angular momentum of the rotors? Now, the rotors have some angular momentum, uh, but the total angular momentum of the system has to be zero, conservation of angular momentum. So something else has to rotate in order to compensate for the fact that the rotor suddenly acquired some angular momentum. What do you think must rotate in the opposite direction to make the total angular momentum zero? The answer is the body of the helicopter. So if a if the blades of a helicopter start rotating in one direction, conservation of angular momentum would make the body of the helicopter rotate in the opposite direction. So that would be a problem, obviously, because you don't want the body of the helicopter to rotate while the helicopter is flying. So that is prevented by using a tail rotor. And that is the reason that helicopters have tail rotors. So the tail rotor exerts an torque which prevents the body of the helicopter from rotating uh, in the opposite direction. It's quite possible that so sometimes the tail rotor of a helicopter might get damaged, or in a war situation, it might get shot. Uh, that's quite fatal for a helicopter, because if its tail rotor is stops working, then the body of the helicopter does start rotating in the opposite direction.
All right, so let me show you an example of that. This is the video that's linked in the PowerPoint. So we can see this helicopter coming in. You can see its tail rotor. Unfortunately, the tail rotor clips the fence here, and the body of the helicopter starts rotating. Fortunately, it looks like everybody is okay, in maybe a little bit injured.